So in this lecture, we are going to like learn about types of damping systems. So damping systems can be divided into two types. First one is first one is first one is undamped. First one is undamped system, and second one is damp damped system. So in undamped system, damping is absent, so there is no damping in undamped system, and the damping factor is equal to 0 for undamped system. In damped system, the damping factor is greater than 0. So we can divide the damped system into three types according to this situation. So the first type is when damping factor is less than 1. Second type is when damping factor is equal to 1, and the third type is when the damping factor is greater than 1. So when damping factor is less than 1, we call it as an underdamped system. When damping factor is equal to 1, then we call it as a critically damped system. And when damping factor is greater than 1, we call it as a over damped system. So let's discuss one by one. So let's first start with erasing this whole thing. So the case one is let's understand about underdamped system. That is when the damping factor is less than 1. So the differential equation, we can write it as d1 of 2 is equal to damping factor times the natural frequency plus minus under root of damping factor dot omega n square minus omega n square. Now further solving it, d1 of 2 solution minus zeta omega n plus minus omega n under root damping factor square minus 1 minus damping factor omega n plus minus iota omega n 1 minus damping factor square. So the region of interest of our equation is minus damping factor omega n plus minus iota omega d. So this is the region of our interest of this equation. So we can here the omega d, that's the damped frequency, is equal to natural frequency multiplied by under root of 1 minus damping factor square. So this is the damped frequency. Now moving forward, let's find out the complementary function for this thing. So complementary function for this thing is exponential of minus damping factor omega n dot t multiplied by a cos damping frequency t plus b sine omega d t. So let a equal to x dot sine phi and b is equal to x dot cos phi. So solution of x, so solution of x equal to complementary function, that is CF. So x is equal to x dot e power minus damping factor omega n t multiplied by in bracket sine omega dt plus phi. So so omega dt plus phi, we can say it, this is the frequency of oscillation. So this is the frequency of oscillation, and this whole thing is the displacement. This whole thing is the displacement equation. Now moving forward, the amplitude of the displacement is equal to the amplitude of displacement is equal to x dot e power minus damping factor dot omega n dot t. So this is the amplitude, and here amplitude is equal to function of e power minus t, that is exponential power minus t. So damped natural frequency so damped natural frequency, that is omega d, is equal to natural frequency, that is omega n, multiplied by under root of 1 minus damping factor, that is 1 minus u square. So it is in this so it is valid in the case of when the damping factor is less than 1. Now let's calculate the damped time period. So damped time period, that is TD, is equal to 2 pi by damped natural frequency, that is omega d. Now let's solve this equation further. So let me raise this thing first. So the um, damped natural frequency is given by the equation omega d equal to omega n multiplied by 1 minus damping factor square. So let's solve. Let's bring omega n to left hand side. So it will become omega d by omega n is equal to under root of 1 minus damping factor square. Now in order to remove this under root sign, we are going to square both sides. That is omega d by omega n square is equal to 1 minus damping factor square. So after further simplifying, we are going to get omega d by omega n omega d by omega n square plus damping factor square equal to 1. So this is the equation of circle. So let's plot. So when we are going to plot like this equation, that's omega d by omega n square plus mu square equal to 1, we are going to get the curve something like I'm going to plot now. Okay, so this is erased. So you're going to get the curve something like this. So on y-axis there is omega d by omega n, and on x-axis there is the damping factor, and the curve will look something like this. This is 1, this is 1. So as you can see that as the damping factor increases, the ratio of omega d by omega n also decreases. So for this condition, the ratio of omega d by omega n is less than 1. So we can say the damped frequency is less than the natural frequency. So this is our main takeaway. So this is the main takeaway from this lecture. Now let's plot the graph between the displacement with respect to time. I'll make this thing first. So let's plot the graph between the displacement and versus time. Displacement versus time. So the graph will look something like this. So in x direction there is t, and in y direction there is displacement x. So so this is the amplitude, that is, we can say it is x naught. This amplitude is x1. This amplitude is x2, and this amplitude is x3, and so on. So the equation of, so this is envelope, this thing is envelope. So the equation of envelope, so equation of envelope is x dot e power minus damping factor dot omega and t. Now let's calculate the ratio of successive amplitudes. Now moving to the another point. Let's calculate the ratio of successive amplitudes. So we can calculate the ratio by like x naught by x1 is equal to x1 by x2 is equal to x2 by x3 equal to dot 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 equal to xn by xn plus 1, which is equal to e power lambda, which is equal to constant, e power del equal to constant. So the del equal to 2 pi multiplied by the damping factor divided by 1 minus damping factor square. So in order to calculate the logarithmic decrement, let me use this thing first. So let's calculate, find out what is the logarithmic decrement. So logarithmic decrement. So x naught by xn is equal to x naught by x1 multiplied by x1 by x2 multiplied by x2 by x3 multiplied by x3 by x4 dot dot x power n minus 1 x power n. So we have studied that x naught by x1 is equal to e power del. So in both cases, like we can e power del multiplied by e power del multiplied by e power del multiplied by e power del dot 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 e power del. So after simplifying, we are going to get x naught by xn is equal to e power n del. So here, taking log both sides, we are going to get and further simplifying, we are going to get n del is equal to logarithmic of x naught by xn. So out of further simplification, we are going to get del equal to 1 by n logarithmic of x naught by xn. Now let's solve further, and let's establish the relationship between the del and the damping factor. So let's move further for more calculations. I think that you people are not worrying while going through these steps. So just take a break if you are surpass your threshold. So let's further solve. So del square divided by 4 pi square is equal to damping factor square upon 1 minus damping factor square is equal to 1 minus damping factor square by damping factor square is equal to 4 pi square divided by del square is equal to 1 minus damping factor square minus 1 equal to 4 pi square del square. So 1 by damping factor square is equal to 1 plus 4 pi square divided by del square equal to 1 by damping factor square is equal to del square plus 4 pi square divided by del square. And further solving, damping factor square is equal to del square divided by 4 pi square plus del square. And after further solving, we are going to get what we are seeking for, that is the damping factor is equal to del upon under root of 4 pi square plus del square. So this is the relation which we are seeking for, which is important relation. Now moving forward, keep in mind stuffs. So let me read this thing first. Okay. So in an underdamped system, in an underdamped system, the amplitude will decay exponentially with respect to time. So displacement will be harmonic in nature, which have time period, having time period t is equal to 2 pi by omega d. So the ratio of another thing you should keep in mind that okay, so another thing you should keep in mind that the ratio of successive amplitude will be constant since x0 by x1 is equal to x1 by x2. Therefore these amplitudes are in geometric progression, that is GP. Logarithmic decrement method is used to calculate calculate damping factor which denote the amount of of damping present in a real physical system. So now let's forward to the next topic, that is the critical damping, and this is the last topic for this lecture and for this section. So without doing delay, let's move forward in the same lecture. So this one was the lengthy lecture, I think. In comparison to other lectures, I think so. So let's move forward. Okay, so now let's talk about the critical damping. So in critical damping, the damping factor is equal to 1. So in this case, we can say that the damping factor is equal to C by 2m omega n. So after substituting the damping factor equal to 1, we are going to get critical damping coefficient, that is C comma C 2m omega n. So we can say that Cc is equal to 2m omega n. So let me write this thing first. So this is equal to sine. So after further simplifying, we can say that it is equal to 2 under root km. So here Cc is the so this is the expression for critical damping coefficient. So we can say that the damping factor is equal to the ratio of actual damping coefficient by critical damping coefficient. See, C is the actual damping coefficient and C base C is the critical damping coefficient. So this is also called as damping ratio. Let's take the important takeaway from this last lecture. Let me erase this thing first. Okay. So now let's find out the solution for something in this case. So the differential equation form is equal to minus of omega n. So solution of x is equal to function of t, that is the complementary function. So x is equal to c1 plus c2t multiplied by e power minus omega n t. So here you can see that x is the function of e power minus t. You should note that the time period will not exist. So in this case, time period will not time period will not exist. Time period will not exist. Hence the motion. Hence the motion. Hence the motion is aperiodic in nature. Aperiodic in nature. You should remember that for critical damping case, let me raise this thing first. So for critical damping case, for this system, for critically this system, the system will not oscillate. The system will not oscillate for critical and overdamped case. The system will not oscillate for critical and overdamped case. Critical damping is the smallest. Critical damping is the smallest amount of damping provided to the system for which there will be no oscillation in free vibration system. So you should note that in overdamped system, the motion will be aperiodic in nature. Now let's end this lecture with some plots. So let's plot some graph. Okay, so in x direction there is time, and in y direction there is some displacement. So for critically damped system, the graph will look something like this thing. So this is for damping factor equal to 1, and this is critically damped system. The graph for overdamping looks something like this. So in this case, the damping factor is greater than 1, and this is called over damping system. And the last plot is when the damping factor is less than 1. So the plot will look something like this, and this is the case for when the damping factor is less than 1, and it is called under damping system. So this marks the end of this section and this lecture.